Okay, we have covered all of the requisite generative adversarial network theory. We've downloaded our data set. Now it's time to actually use that data set of apples or whatever category of hand-drawn images you downloaded to build our generative adversarial network and produce machine-manufactured replicas in the style of the category that you selected. So if you followed my installation instructions, then you start off in a Jupyter notebook in the home directory. You can pop into the work directory and then into notebooks. You'll find in there that the Generative Adversarial Networks notebook is available there for you and complete, and all of this code runs. But we are going to recreate this notebook here step by step to give you a sense of every line of code and why it's important. By having to type all this stuff in, it forces me to explain everything and not skim anything. So let's create a new notebook, in my case in Python 3 here. We're going to give this notebook a title. So for me, I'm going to call it Demo GAN, but you can call it GAN or Generative Adversarial Network or whatever you like. For using the Jupyter Notebooks, I provided a slower intro in my Deep Learning with TensorFlow live lessons in the first Jupyter Notebook that we use there. So I'll move a little bit more quickly here. The first thing that we're going to do is give this a title. So I'm going to press the 1 key to create a markdown cell of the highest level of title. And you can call it a GAN or whatever you like. And in this notebook, we're using code based directly on my colleague Grant Baileveld's code. And in the original notebook, I provide links to that. And his is derived from this gentleman, Raoul Atienza. And then, of course, the data that we're using in this are provided by Google, as we showed previously. So those are the attributions for this notebook here. So the very first thing that I need to do on my machine, which you may not actually need to do on your machine. So this is only if you're using GPUs, but I want to show you this handy little trick. So I'm going to create a subheading by pressing 4, and we're going to select our processing devices. So I've given this title Select Processing Devices because we're going to import the operating system library, and we're going to use it. Specifically, we're going to specify an environment parameter, which, again, this is only relevant if you're using a GPU on your machine. But you tell it that, so typically, if you have multiple GPUs on your machine, and this server that I'm running this notebook on does have multiple GPUs, so I run into the issue that those devices can have a random order unless you specify that you want the PCI bus ID to be the order that they're in. By setting the CUDA device order parameter specifically to PCI bus ID instead of just the randomly generated values, then you can pop over to your machine. So this is a terminal window looking at the deep learning server that I built that's running 2 GPUs on it, 2 NVIDIA GPUs, and I can type NVIDIA SMI and have a look at the GPU orders. So there's a GPU 0 and a GPU 1. So I can see that GPU 0, its memory is already loaded with another task that I'm running. So for this notebook, I'm going to specify that I want the only GPU 1. So GPU 1 here, nothing is in its memory. All of its memory is free as opposed to being full. And so that's the GPU that I want to use, and it'll be dedicated to this task. So we do that by saying that the visible device is GPU number 1. Now, so if I switch this to 0, then I would be running it on this GPU, which actually already has, it would be silly to run it on that GPU. I might not even be able to allocate this network into memory when we build it. The other option that you have is you can actually leave this empty and then it will only run on the CPUs on your machine. So if all of your GPUs are already in use, then you could use your CPUs. Typically, the CPUs are orders of magnitude slower on their own than supplemented with a GPU. So I wouldn't typically do that. So I'm going to leave this as 1. Now we're going to load our dependencies. So this will be relevant to everyone. In fact, everything else that we type is going to be relevant to everyone. So for data input and output, we're going to use the NumPy library for working with numbers. If you hadn't run the cell up above, then you're going to need to import OS just for creating some directories later on for outputting our results. For deep learning, we're going to use the Keras high-level API on top of TensorFlow. In particular, we're going to need 2 model types. So the sequential model type is probably is definitely familiar to anyone who's done my live lessons before, because that's the standard kind of model that you build where each layer passes into the next sequentially. There's another option called the model with a capital M, which allows you to specify more than just layers passing sequentially one into the other. So we're going to take advantage of that here as well. At the end of my natural language processing live lessons, I use that model parameter to create a network with very sophisticated architecture. So check that out if you're curious about the kinds of things that you can do with that model parameter. We're also going to import a number of different layer types. So most of these are going to be familiar. So an input layer, that language won't be unfamiliar, but if you're used to only using the sequential way of building a model, you didn't need to specify the input as a specific layer. Now when we use this model way of building models, we do need to specify the inputs specifically. We're going to use dense or fully connected layers, as we pretty much always do in our deep neural networks. We're going to have convolutional layers. So those convolutional layers will play a prominent role in our discriminator, which will be taking in images and identifying features in those images to guess whether they're real or fake. We're also going to use batch normalization. So batch normalization allows us to keep the mean and the variance of the output of each of our layers stable, which is important because we're going to be building such a deep adversarial network here with the generator feeding into the discriminator. There's so many layers that we want to use batch normalization to make sure that we don't have the values, the output of our layers experiencing something called covariate shift. We'll get into that a bit more later. We're going to use dropout to avoid overfitting, and we're going to use flatten to convert multidimensional, so 2 or 3-dimensional outputs into a single array for our dense network. So these are all terms that I've used in my live lessons before. These are all layer types. But we're also going to use a few new types of layers in this notebook as well. So one of those is the activation layer. So the activation layer, previously we've always just specified whether we want to use sigmoid or tanh or relu as a parameter when we call a layer type. In this notebook, we're going to want to be more specific and dictate explicitly when we want that activation to happen relative to other things that are happening in the layer like batch normalization. So we're getting a bit more granular than we ever have before. We're going to use the reshape layer, which is unsurprising. It's just to change the shape of the data, so the dimensions. So say you could reshape from 3 dimensions to 2 dimensions of that kind of thing with the reshape layer. Here's a doozy. We're going to use the conv transpose layer. So this is what I was referring to as a deconvolutional layer here in the generator. So this kind of layer, so transpose, conv2D, deconvolutional CNN, these are synonyms to describe the inverse of a convolutional neural network. We'll get into that in a bit more detail when we start typing out the code later on. And we're also going to use this upsampling 2D, which is like the inverse of max pooling. So with max pooling, we're reducing the dimensionality of layers. So that's something that we got into a lot with our machine vision applications in my Deep Learning with TensorFlow Live lessons. The upsampling 2D is going to be used in the generator to abstract the features into a number of pixels that is the same as our real images, so that the fake and the real images have the same dimensionality. And finally, our optimizer is going to be RMS prop. So RMS prop is an alternative to Atom as a second order gradient descent optimizer. And so we haven't used it before. It works in a similar kind of way. It's a little bit older. And here we're going to be using it effectively. It could also be the case that Atom would work well. You guys are welcome to try using that as your optimizer instead at home. Finally, we're going to be outputting some plots as we go here. So to do that, we're going to use pandas for manipulating data frames and matplotlib to actually output our results. And then we're going to use the matplotlib inline magic to have the plots output in the Jupyter Notebook. Now comes time to load our data. Your NumPy file should now be visible in your QuickDraw data subdirectory within the TensorFlow Live Lessons directory that would have been created if you followed the installation instructions for these live lessons. And in there, I have this apple file or this bulldozer file to choose from. I've used the apples a million times. I'm going to use them again here because they're reliable for me. More complex shapes like bulldozers, you might have to train longer than a simple shape like an apple like I want to use in this demo. Okay, so we need to specify where our input images are. So I'm going to say that the input images are in the QuickDraw directory, and I'm going to use the apple MPY file. And then we can actually load in the data with the NumPy load function. So these images are 28 by 28 images, the same as the MNIST digits that you would have become familiar with if you did my Deep Learning with TensorFlow live lessons. And these are also grayscale, and they're grayscale bitmaps that have been pre-processed by the QuickDraw people to have the cartoon be, the hand-drawn image be in the center of the 28 by 28 bitmap. So there's been a bit of pre-processing on these, but not a lot. And so we can have a look at the shape of the data. Because these are 28 by 28 images, they've flattened them into a 784 by 1 array. So we're going to have to fix that in a moment. But this other dimension, this other shape dimension, this is the number of cases of hand-drawn images that you have for your category. So the apples category at the time of filming has 145,000 hand-drawn apples in it. It's a pretty rich data set. And we can have a look at any one of those. So I'm just going to pick a random number here, 43, 43, and you can have a look at these values. So you can see they range from 0 up to 255. And so 255 represents a black pixel, whereas zeros represent white pixels. In a one-dimensional array, it's difficult to see what's happening in there. So let's pre-process these for our purposes. So we're going to divide by 255 so that all of our pixel values range from 0 to 1. In general, in machine learning, having your inputs range from 0 to 1, standardizing them like that is a good idea. And we're also going to reshape our data with the NumPy function here. And we're just going to reshape them to those 28 by 28 pixel shapes that we are used to, or that we need, actually, for our convolutional network, for our discriminator to train on. We don't want to train, we can't apply two-dimensional convolutional layers to the 784 by 1 array. If we want to apply the more powerful convolutional network than just using the dense or fully connected networks, then we want to have our images in the 28 by 28 pixel format. There's a fourth dimension here, which I've just filled in with 1, because these images are grayscale, so we don't have a color dimension. But if you had a color dimension, then this would be a 3 to represent the 3 different color scales. Okay, and then we're going to create these image width and image height variables for reuse later. And these are simply going to be the shape of the data, the width and the height. And yeah, now we can have a look at the shape of our data now. So now they are 28 by 28 pixel images. We still have, of course, exactly the same number of them. And so now when we look at that same random image, you can see that it's now 28 by 28 because we have these nested arrays, and the pixel values range from 0 to 1. So that's great. That's exactly what we wanted. And we can also have a look at our data here. So we can use the plot image show function here to look at that apple, or whatever image you have, and see what it looks like. Set the color map to grays. I made a typo of this comma being missing. So there we go. How about that apple? Man, I'm going to wear that joke through. So this is a human-drawn apple. This is one of the 150,000 hand-drawn apples that we have in this data set. That's cool. We've loaded in all our data. There's just one last step for this sublesson, and we're going to define our discriminator network. So this is all going to happen in a single function. So we're going to define our function called discriminator builder. And this function is not going to have too many parameters. We're going to specify the width, this kind of default width of our neural layer. So this is a hyperparameter. If I was being more particular, I would be specifying my hyperparameter at the top of the file. That would be a good practice. And we're also going to specify how many, the proportion of neurons that we're going to drop out on a given training update. So I'm going to set that dropout to 40%. Okay, now within here, we're going to define our model. So the very first thing that we need to define is our inputs. So define inputs. That's going to, we can call it inputs, and we use our input function in Keras to create it, and we're going to specify that these images have the width and the height and the color depth of 1. So, we're just telling the network what to expect. These are the same parameters as we already knew from above in the notebook. And now we can actually define our convolutional layers for processing these inputs. So our first convolutional layer, conv1, is going to be a convolutional layer, so specify that. This first layer is going to have 64 neurons in it. So I'm leaving this as width times 1 because later layers we're going to specify multiples of 64. And so this is just kind of for that consistency. We are going to say that we want to have a 5 by 5 filter size. So the convolutional filter that's passing over the image in this first convolutional layer is a 5 by 5 filter. And we want it to have a stride length of 2 by 2. So we can specify that with a single 2. And we want our padding layer after layer to remain the same. Our activation function is going to be ReLU, rectified linear units. That is my go-to. Okay, and then now, because we're not using a sequential model, because we're using a capital M Keras model, we need to specify all the way through what is being passed into a given layer. We do that with a second set of parentheses. So passing into this layer is the inputs layer. And we're going to add dropout to this layer as well with 40% dropout, and passing into that just, itself. So this input is passing into this convolutional layer, and then this convolutional layer, I'm not renaming it because otherwise it would get really tedious just renaming the same layer because we had a dropout. It start to become pretty ugly code. Okay, now we're going to add a second convolutional layer by copying and pasting that layer. We need to rename it convolutional 2. And this time, we're going to have 128 neurons in the layer. So we're gradually, our discriminator is going to have gradually more filters as we go deeper with our convolutional layers. So we're allowing the more abstract layers to have more types of things that they can be looking for. So the first layer is going to be looking for 64 different kinds of elementary features in the image. And then the next layer is going to be looking for 128 recombinations of those simple features. There's a million different ways. The number of convolutional layers you have, the width of the layers, these are all hyperparameters that could probably be better by playing around with them. But I know that this configuration works. The broad idea here being that we're expanding the number of possible features that we're looking for as the abstraction increases convolutional layer over convolutional layer. Okay, our third convolutional layer is going to be similar again, except we got to rename it conv3. Ooh, we got to also be careful to have our inputs into the layers match as well. So I didn't set, so convolutional layer 1 should pass into convolutional layer 2, and convolutional layer 2 should pass into its own dropout layer. Then convolutional layer 2, we need to pass into convolutional layer 3. The only parameter that we're going to change in this layer is again doubling the number of filters in the layer, so multiplying the width times 4 now. And we're going to call this convolutional layer 3. And we're going to pass convolutional layer 3 into its own dropout layer. And then the final convolutional layer 4, it's going to take as input the convolutional layer 3. And its width now is going to be doubled again, so times 8. The strides parameter is actually going to decrease as well. You're welcome to try with 2, but we got better results with a stride length of 1 in this layer. We're going to have dropout in this layer as well, and we're going to flatten after the dropout. So here's another way that you can chain these together, just to kind of keep the code tidy. So this is just indicating that this output, this conv4, we're going to apply dropout to it with the same 40% as all the other layers, and then we're going to flatten from 2 dimensions or 3 dimensions, depending on whether you have monochrome or color images or not, into a output layer. So this output layer, we can give it a little title, is, we only have real versus fake here, so we can capture that binary value from 0 to 1, so we only need one output neuron, and its activation will be sigmoid. So recall that sigmoid neurons are an activation function that provides a value from 0 to 1, like a probability, so that's great. And we're passing into it this conv4 right there. Now we have to actually define our model. So with the sequential models, you typically do that at the top. With the capital M Keras model, you do that at the bottom of the definition. So we say that our model is equal to capital M model, which takes its inputs as the inputs layer, and its outputs are the output layer. And then we can pop out a model summary and return the model. Great. So that's what our discriminator convolutional neural network looks like. That's going to discriminate our real apples or whatever you downloaded from our fake apples. And to have a look at that, we can create an instance of it by calling the function that we just created. And then we can have a look at the shape of our network. So our discriminator model has 4.3 million parameters in it. So our adversarial network is going to have way more because we still have to add in all these parameters from the generator. And you can see because we were exponentially increasing the number of filters layer by layer, we have way more parameters as we go deeper into the network. So the final step is to compile our discriminator. So this discriminator is going to be operating on its own to discriminate real from fake, and then we freeze its weights and we use it as a component of our adversarial network. But in that first part, where we're having it discriminate real from fake, we need to use it as a full model. So to do that, we need to compile it. So we'll say discriminator.compile, and we're going to have our classic binary cross entropy loss. So that's this cross entropy cost function that we know is very efficient for deep learning. And it's binary because we just have the 0 or 1, the single sigmoid neuron output. We have the optimizer of our choice, which can be RMS prop. There's a learning rate parameter that we have to set here. We found that the value 0008 worked pretty well for us. So you can try that as well. And then we have a decay parameter so that our learning rate slows down. And so typically when we've used Atom in my previous live lessons, we didn't specify the decay explicitly. Here with RMS prop, we are going to, so this means that we're going to have, with each step of learning, our learning rate will slow down from this starting point. And finally, we're going to have a new parameter here, at least new for my live lessons, the clip value parameter. So this clips, so the gradient is how quickly we can be learning, and we're going to clip that at 1 so that it can't get going too fast. That will ensure that the network doesn't jump around, that the parameter values don't jump around too much. And finally, we're going to output accuracy. So the percentage of images that are correctly classified as real or fake, that accuracy will be how we assess. As humans, it doesn't really matter to the learning algorithm, but as humans, it's kind of nice to see how accuracy is performing over time. It's something that means a lot to us. So that's the end. We've defined our discriminator. Up next, we're going to define our generator and tie them together after that into this generative adversarial network.